to Robot Lab live event from University of Surrey campus. We are a team called Star Lab that stands for Space Technology for Autonomous and Robotic Systems Laboratory. I'm the head of the lab, Professor Yan Gao. The rest are our team members who are supporting the demo today for you.
Hi everyone, my name is Sam. I'm a postdoc researcher on orbital robotic. And my research mainly focuses on AI, autonomous GNC, guidance, navigation, and control.
Hi everybody, Alexander is here. I'm a lab technician. I'm responsible for maintaining hardware running and help Sam with his research.
Good afternoon everyone, I am Rohit Nikam, a postgraduate student in space engineering, and basically I am doing here a technical support role to support some projects and all the sorts.
Hi everyone, my name is Lisa. I'm an undergraduate in MEng Aerospace Engineering, and I'm a summer intern here at the Star Lab working on the robotics optical test bed.
Excellent. So what we'll do, I'm going to start with some introduction, background setting for the demo, and my team, they're going to move to the demo station and start the preparation of the work. Thank you guys, see you in a bit. So now I'm going to, first of all, using this model here to help explain the space mission background that help describe and help you to understand why artificial intelligence and robotics is a very critical technology that we're using to support these future missions. So here you are saying a spacecraft that represent future core piece of hardware for the missions, then they can help to deploy the base infrastructures for large space telescope. So instead of launching a monolithic space telescope, which is going to be expensive and bulky to do, we're able to launch those space mirrors in small pieces like a mirror segment. And with the help of robotic arms on board the future spacecraft, we can perform and peak place. So you can envisage that these robotic arms will be, autonomously identify space mirror segments from the mother satellite and transport it to the base structure after it's been deployed. So they can then form a much larger scale space optics devices. And here we have a model of the mirror segment in almost the true size, so you can appreciate the real scale of the space mirror, and they will be sitting on top of structures like this. Again, it's almost in the real scale, and there's a part of the structure which contains a mechanical part for the docking mechanism to work. And the other half of the docking naturally will sit on any effector of the robotic arm deployed from a servicing satellite that can perform the identification of the mirror segment structure in real time in a space environment and perform the approaching and docking autonomously. And in this process, which is of course a very critical process during the mission, we have to rely on robotic vision, some autonomous AI-based algorithms to achieve this very successfully. And this is the phase of the mission we are trying to demonstrate to you in the laboratory today in real time. So I hope that's a reasonably clear introduction, and I'm going to move the camera now to our test bed in the lab, and we can start conducting the experiment. See you in the other end.
will guide you through how our experiments works in terms of technicality. So basically what we have here is a setup of two robots. We have a service arm on my right, basically, the white robot that you can see. And that robot has got half of the docking mechanism attached already to it instead at the end effector. And we have got numerous sensory system and visual-based camera system that transfer all the video in a live mode into our control system. Basically, we use AI, a different type of machine learning algorithm to pinpoint the position, the exact position of our target arm, and do have a very smooth docking operation. On my left side, what you see is the segment of the mirror that Professor Young already showed it to you in the introduction part. So basically, that structure should have the mirror on top of it. And it's been attached to another robotic system. In this part of the robot, we are actually using a specific software program in ROS that mimic and replicate the microgravity in orbit. So basically, that section of the mirror can freely move around, and it's like it's floating in orbit. On top of each of the service arm and target arm, what you see is some glowing balls, and those glowing balls are part of a bigger system that you probably cannot see in the video at the moment. There are like several cameras around the lab, and those actually measure the exact positions of both target and service arms in the simulation run, and it helps us to actually know how what quality and precision and accuracy the docking system works. Basically, it's some kind of ground truths for us to validate the whole system together. So that's it from me. Without any extra talking, me and my colleague actually starts initiating the experimental run. Thank you.
So currently the target proximity guidance navigation control phase. We're using onboard algorithm is going to see how the key features are in this field of view, and now there's a third view being added, which allows you to see more precisely how the approaching and docking is in action. And also you can see those orangey color dotted features on the right-hand side of the screen because that was used as the ground truth for the comparison, so we can evaluate the performance afterwards in terms of the precision accuracy of the navigation. And now the physical connection has also been deployed. It might look a bit dark on the screen because that's just the color of it. But the mechanical connection is the follow-on step. Once the onboard software confirm it's a success, approaching and docking, and to deploy the actual connector, and it's now physically connected and fastened. And now what we are going to show you is a final phase of the step. You're seeing my colleague now approaching the service arm. What he's doing right now is he has to unlock a safety button on the servicing arm to allow free motion, because at the moment the servicing arm has a safety mechanism built in, but in the real mission it does not need to be mechanically unlocked, but just because of the safety issue in the lab setting, it has to be a mechanical lock in this case. So what Sam is now doing, he's actually not controlling anything. All he's doing with his hand is to unlock that safety button. But what he can show us just now is a free motion of the servicing arm with now the integration of the target object. And as what he was clearly showing just now, there's a complete free motion there, which doesn't require any actual force to allow the withdrawal of the target. So we restored the position of the target, and then I think we have reached to the point we need to allow questions from the audience, if any. testing the microphone.
Can't hear anything.
Just testing.
When you are on the screen, it is coming.
University of Surrey campus. We are a team called Star Lab, that stands for Space Technology for Autonomous and Robotic Systems Laboratory. I'm the head of the lab, Professor Yang Gao. The rest are our team members who are supporting the demo today for you.
Hi everyone, my name is Sam. I'm a postdoc researcher on orbital robotic, and my research mainly focuses on AI, autonomous GNC, guidance, navigation, and control.
Hi everybody, Alexander is here. I'm a lab technician. I'm responsible for maintaining hardware running and help Sam with his research.
Good afternoon, everyone. I am Rohit Nikam, a postgraduate student in space engineering, and basically I'm doing here a technical support role to support some projects and all the sorts.
Hi everyone, my name is Lisa. I'm an undergraduate in MEng Aerospace Engineering, and I'm a summer intern here at the Star Lab working on the Robotics optical test bed.
Excellent. So what we'll do, I'm going to start with some introduction, background setting for the demo, and my team, they're going to move to the demo station and start the preparation of the work. Thank you guys, see you in a bit. So now I'm going to, first of all, using this model here to help explain the space mission background that help describe and help you to understand why artificial intelligence and robotics is a very critical technology that we're using to support these future missions. So here you are saying a spacecraft that represent future core piece of hardware for the missions, then they can help to deploy the base infrastructures for large space telescope. So instead of launching a monolithic space telescope, which is going to be expensive and bulky to do, we're able to launch those space mirrors in small pieces like a mirror segment. And with the help of robotic arms on board the future spacecraft, we can perform and peak place. So you can envisage that these robotic arms will be, autonomously identify space mirror segments from the mother satellite and transport it to the base structure after it's been deployed. So they can then form a much larger scale space optics devices. And here we have a model of the mirror segment in almost the true size, so you can appreciate the real scale of the space mirror, and they will be sitting on top of structures like this. Again, it's almost in the real scale, and there's a part of the structure which contains a mechanical part for the docking mechanism to work. And the other half of the docking naturally will sit on any factor of the robotic arm deployed from a servicing satellite that can perform the identification of the mirror segment structure in real time in the space environment and perform the approaching and docking autonomously. And in this process, which is of course a very critical process during the mission, we have to rely on robotic vision, so autonomous AI-based algorithms to achieve this very successfully. And this is the phase of the mission we are trying to demonstrate to you in the laboratory today in real time. So I hope that's a reasonably clear introduction, and I'm going to move the camera now to our test bed in the lab, and we can start conducting the experiment. See you in the other end. Thank you.
Hi everyone, Sam here again. So I'm gonna go through the experimental procedure and explain to you what happens here. So basically we have got two parts in our experiments. One of them is the service arm on my right, that you can see the white robot. The service arm has got half of the docking segments attached to as an end effector that you can see here. And it has got a few cameras and sensory system to basically that sends those captured images and live data to onboard computer and generates the autonomous trajectory and docking system that we require for this specific operation to assemble the segments of the mirror for the telescope. On my left side, what you see is the structure, that segment of the mirror that Professor Young already showed to you in the introductory part. There is another docking system, the other half has been attached to this part. What we have here on this robot is a software-based system that mimic and recreate the microgravity for in-orbit situation and in-orbit conditions. So basically that segment, that part is free to float around and move around. So as you can see that I can actually rotate it or do whatever I want to it. So it is very important part to show that this segment and this part of the docking is free to move and float around. What you see on top of both of the arms is these glowing balls that you can see on the screens. These are part of the bigger system that you probably cannot see in our video. These are lots of cameras attached to around the lab. That system actually pinpoints the exact position of each of the target and service arm at any moment. So in a real-time live mode. So we use that as a ground truth to actually make sure and validate that the docking happens in a proper way that we expect to do that. So I don't keep you that much. Let's go through and show you how the actual system works.
Now screens, on the screen there are two view angles, and now the docking of the target object has been completed, and therefore the system is actually initiating autonomous algorithms on the servicing arm, guided by the visual system. So basically what we are saying here, you can see multiple angles of the say from the screen, the global view, which shows approaching from the service arm to the target. On the right hand side, you have the close-up view of the target through the cameras on board the spacecraft, robotic arm, and then you're also seeing a very precise image that represents the technique from the algorithm in real time itself. And what you can see is how we could monitor the performance through those ground truthing sensors, which Sam had introduced earlier. those orange colored dots represents the K data points that's collected from the ground truthing system that we can use later on to validate and verify. And now the mechanism, those locking mechanism is also being deployed. They look a little bit dark on the screen, unfortunately, because they're all black colored. But basically, the algorithm has been informed that now the mechanical connection is also completed. And now my colleague is back on the side, because what he's now going to show you is a final step of what we call the rigidization of the final system. So what he was doing there is he basically unlocked the safety switch on the servicing arm, which is just a mechanism on board the servicing arm for safety reasons in the lab setting. But in reality, what's going to happen is this switch will be programmed to unlock at that stage. So you can see basically the motion, the free motion, complete free motion from the servicing arm carrying the target, even though the target is now mounted on an actual physical arm in the ground test bed, is still very successful and safe. I think there are a few questions coming through, which we will try to answer. So it's the question, just read it out. There are two black and white markers around the right-hand side of the robot. Oh, okay. I think the question relates. Okay, so I'm just reading out the questions, allow our researchers from the lab to answer it. So Sam, would you like to take this one?
Hi everybody. Relating to that question.
Oh, do you want to go to?
Oh, in front of the camera. Okay. So
yeah, I think we do.
Can you see me now? All right. That's great. So basically, those two things that you see on the side of the robot are the QR codes. So they look like normal QR codes, but they have been especially designed and created and measured precisely to use as a fiducial marker. So our autonomous system actually read those QR codes, generate the specific orientation that associated with each of the QR codes, and measure the distance from the camera. And we have got the translation from the camera to the end effector, that we know that how long and in what distance actually and direction move the robot to do the actual docking. So in our today experiment, we are using those QR codes on the side of the robot as the main reference for guidance, navigation, and control. Thank you.
Thanks, Sam. That's very helpful. I think just for the background, because this question is very relevant to some generic design for orbital robotics. So this particular application we're demonstrating today is classified as docking with what we call cooperative targets. So meaning those targets are something being part of the design of the mission. So we can design features on the target so that we can recognize. But people from previous year's demo could probably remember we have demonstrated techniques to grasp non-cooperative targets such as debris, space debris. Therefore, it's not possible to use fiducial markers. Well, we have to use completely artificial intelligence to help recognize and detect docking points. But this is an excellent question. Okay, so we're going to now reset and come back in a few minutes with the last run of the demo. See you very soon. welcome to Robot Lab live event from University of Surrey campus. We are a team called Star Lab, that stands for Space Technology for Autonomous and Robotic Systems Laboratory. I'm the head of the lab, Professor Yan Gao. The rest are our team members who are supporting the demo today for you.
Hi everyone, my name is Sam. I'm a postdoc researcher on orbital robotic, and my research mainly focuses on AI, autonomous GNC, guidance, navigation, and control.
Hi everybody, Alexander is here. I'm a lab technician. I'm responsible for maintaining hardware running and help Sam with his research.
Good afternoon, everyone. I am Rohit Nikam, a postgraduate student in space engineering, and basically I'm doing here a technical support role to support some projects and all those sorts.
Hi everyone, my name is Lisa. I'm an undergraduate in MEng Aerospace Engineering, and I'm a summer intern here at the Star Lab working on the Robotics optical test bed.
Excellent. So what we'll do, I'm going to start with some introduction, background setting for the demo, and my team, they're going to move to the demo station and start the preparation of the work. Thank you guys, see you in a bit. So now I'm going to, first of all, using this model here to help explain the space mission background that help describe and help you to understand why artificial intelligence and robotics is a very critical technology that we're using to support these future missions. So here you're saying a spacecraft that represent future core piece of hardware for the missions, then they can help to deploy the base infrastructures for large space telescope. So instead of launching a monolithic space telescope, which is going to be expensive and bulky to do, we're able to launch those space mirrors in small pieces like a mirror segment. And with the help of robotic arms on board the future spacecraft, we can perform and peak place. So you can envisage that these robotic arms will be, autonomously identify space mirror segments from the mother satellite and transport it to the base structure after it's been deployed. So they can then form a much larger scale space optics devices. And here we have a model of the mirror segment in almost the true size, so you can appreciate the real scale of the space mirror, and they will be sitting on top of structures like this. Again, it's almost in the real scale, and there is a part of the structure which contains a mechanical part for the docking mechanism to work. And the other half of the docking naturally will sit on any factor of the robotic arm deployed from a servicing satellite that can perform the identification of the mirror segment structure in real time in the space environment and perform the approaching and docking autonomously. And in this process, which is of course a very critical process during the mission, we have to rely on robotic vision, so autonomous AI-based algorithms to achieve this very successfully. And this is the phase of the mission we are trying to demonstrate to you in the laboratory today in real time. So I hope that's a reasonably clear introduction, and I'm going to move the camera now to our test bed in the lab, and we can start conducting the experiment. See you in the other end.
Hi everyone, I'm Sam. After a very concise and complete introduction by Professor Young, I will go through the technicality of how our experiments works today, basically. So we have got two different segments here, two different robots here that we used for the autonomous AI-based guidance, navigation, and control and docking system here. So I have got the service arm on my right side, which is your left side on the screen, the white robot that you can see here. Instead of normal grippers and things that you see on the robots, we have got half of the docking system attached as the end effector to it. And on above that, we have got different sensory systems and cameras that basically we record and in a live mode and send data to our onboard computer for machine learning and AI-based recognition of the two QR codes that we have attached here. So basically, what our service arms does, read these QR code, find the exact orientation of these QR code, and we have got a translation and transformation that generates the exact path and distance that it needs to travel and orientation, basically, that our service arm needs to travel to catch and do the docking. On my left side, we have got this segment of the mirror that Professor Young already showed you. Basically, the mirrors goes on top of that one here, and it has got half of the docking mechanism here as well. This robot is has got a very special system, basically. We created a free drive and free movement on it in a way that you already saw how I'm using it, in a way that it mimics the macrogravity condition in orbit. So basically, we assume that this part is already floating in orbit, and the service arm comes and sync itself with this part and do the docking in an autonomous way. These glowing balls that you see on top of both of the robots attached to a bigger system that you cannot see in our videos. There are several cameras on the ceiling here that actually pinpoint the exact position of the target arm and service arm within fraction of millimeters. So it is very accurate. And we use that data to make sure that we have got a validation system as a confirmation, like a ground truth, to make sure that docking happens in a way that we expect. So that's basically everything from me. Let's see how the system works.
Great. Just help to explain what is going on the screen right now. So left and right, you see two view angles of the test bed. Right, so you can see now we're simulating the target object in orbit motion. The target arm is trying to recreate a typical motion in orbit. And this is a phase in the mission where we have to perform a rendezvous with the target in space, where the servicing satellite carrying the arm is going to rendezvous and synchronize its orbital motion with the target. And once that's completed, you can see that the servicing arm will start to initiate, and the visual system start to guide the servicing arm and to approach the target. And it's worth highlighting, this is through a vision sensor that is very simple. It's a monocular vision system and supposed to run very fast on board the spacecraft,
many of you would appreciate that even the modern spacecraft have a very limited onboard processing power because all the hardware has to be radiation harnessed. So it's actually very limited in computation. And you can see that approaching was very successful under the robotic vision algorithm. And it confirmed that the docking is good or safe to proceed. And there's a further window being added now, which confirming that the physical, the mechanical interface and locking is also successfully conducted. It's very interesting to see those yellow or orange colored dots that was detected by our ground truthing system, which Sam introduced earlier. This again a reassurance that the precision accuracy has been successfully achieved for this docking process. So the mission typically at this stage will need to move to a stage that the robotic arm has to withdraw. So meaning it has to move together with the added object to its anti-effector. This is a stage called rigidization, and the reason my colleague is holding a part of the servicing arm is because for this particular arm, due to safety reasons, it has a physical switch that I think, Sam, if you can show where your hands are, which you actually, yes, so your right hand where he was basically pressing a safety lock that allowed the arm to withdraw. So this is not, in fact, in the real mission, there will be some kind of electrical switch that would allow the servicing arm to withdraw the anti-effector now with additional extra parts added to it. But for this testing on ground, due to safety, it is disabled. So my colleagues was basically showing you how this can be achieved. But you can see very well that the rigidization is very successful. It's all safe as it's moved. Okay, so I think we need to move now to the Q&A part, and before we take newer questions, I just want to make sure we answered a previous question that has been left from the last round that we didn't have time to answer. So this was a question about the biggest challenges to have robotics in space. I think it's fair to say that there are actually many challenges to make robotics useful and safe to operate in space. Well, my answer would be that we need to ensure the artificial intelligence we incorporate in the spacecraft is safe to operate, is reliable. So some of the things you've seen today where we use visual guided system to perform the run-do and docking, those algorithms need to be verified, validated offline, first of all, during the design phase. And also there has to be continuously proven to be safe in real time. So for instance, we do have techniques added to the demo today where we could verify in real time some of the sensor data, ensure they're actually safe and genuine and untagged. For example, sometimes there could be security issues, and that could be hacks to the algorithm in space. So those extra measures will be added in cases that we think there might be a risk involved. And other related challenges, I think something being briefly touched on. Well, I was taking you through the demo itself. For example, the algorithm need to be very lightweight. Sorry, I have people walking in front of the camera. Yeah, sorry about that. And we need to ensure those algorithms are lightweight. So as you can see from the setup here, there's a very simple camera. It's a monocular camera we use. It's a single lens camera, which reduce the data demand on onboard computer, which is always ongoing challenge. All the hardwares has to be radiation proof. Therefore, they tend to be very expensive in its development. So we have to ensure that the algorithm we invented, we added to existing system is going to be compatible with the hardware constraints. I'm just looking at my team and see if anybody wants to add to that answer. Yeah, I think we have Sam coming to the camera now because he would have something to add. Sam.
Hi, everyone. All right. Professor Young already explained the challenges in space, but the most significant ones already. The other things that we have is different lighting condition, basically, which really affects how the cameras read and can operate in space. So basically, when you are in a LEO, low Earth orbit, we have got every 90 minutes, depends on the actual altitude, but every 90 minutes, 2 hours, something like that, we have got like a whole day, a full day on Earth. So basically, the lighting condition starts from sun in front of you and sun behind you. So basically, you have got different shadows and things that come in. And all these AI-based systems needs to adapt to different lightings within a few minutes. So the condition is changing within a few minutes. And it is really difficult. It's really challenging to set and adjust the whole settings automatically to behave in a way that we expect in space condition. I just wanted to add that to the thing that's already been explained by Professor Young. Thank you.
Did you mention the harsh environment?
Excellent. It's very helpful, Sam.
Second
Hello
question,
guys,
Please.
we're back now. So we're back now. So we're just going to start by answering some leftover questions from the last session. So there's a question I think our researcher Sam is going to help answer. Sam can be, one is to do with the welding, but I guess one thing we could say is that for the robotic system, as you appreciate, it's all various different parts made of different materials, and there's different coating involved to help avoid the co-welding, issue. Sam, do you want to add anything just based on your experience working with such a complicated system?
So basically, we have got space-graded robots that are already been designed and developed in a way that they seamlessly, without any problem, work in a space environment. In our experiment, we are not using any of those because it is a TRL 4 and 5, basically technology readiness level is 4 and 5, but all these problems are being considered before launch. So when you're launching something in a space, we are using a space-graded robot. You're quite comfortable that none of these problems regarding to temperature and a space harsh environment like cold welding is gonna happen. So these are the things that we make sure it's not gonna happen. Yeah.
Thanks, Sam, and thanks, Harry, for the very interesting question. The next question left from the last round is from Abnev, and who asks about the inference for the post estimation because it's running real time. The question is asking about the minimum time that we have achieved in this demo. Sam, if you could comment on
Yeah,
that.
actually, our algorithm output every time that generates the trajectory it's actually output the calculation time for that specific thing. It varies basically on the different lighting condition and different distances that we have. But the quickest one that we could achieve was 0.27. But my experience, because it was not something that we rely on. The thing that we wanted was have a reliable and a smooth trajectory that we focus on. But it's normally between 0.27, which is the quickest one, and 0.5 in average under our condition, lab condition, basically.
Thank you, Sam.
No problem.
This round just put some spice into the real live demo. So I'm going to hand over the mic to Sam and the team. We decided to not repeat the introduction because I think we had that running for a few times. We're just going to go straight to the demo, but we're going to do something more spicy than the few demo previously, just to add some interest or drama into the thing. Because as Sam was saying earlier, one of the biggest challenge he identified being a space engineer is the lighting condition in a space environment is really challenging to manage using any visual based methodologies. So here we're going to show you how challenging and difficult that is. So I'm going to hand over the mic to Simon so that he can take you through those challenges, since we have a relevant question as well from some of the audience.
Right, thank you, Yang. I'm gonna go to, just give me 1 second. I set up my microphone. So we'll go through the experiments once more. The difference this time is we have got, it's very bright now. If you see, I have seen our previously run. I intentionally increased the brightness of the scene like 10 times more, because we have a very powerful spotlight here. So basically, we use that spotlight, and it is a portable one. It moves around the lab. So we use that one to show the position of the sunlight and create different position of the sunlight and test our system. So I put it in a very bright, and I want to see what happens into experiments. I go through the introduction again. What we have here on the right side, on the white robot that you can see, is we replace the normal end effector gripper with the half block of the docking systems as the end effector here. We have got the cameras and the system for AI-based calculation and algorithm for the trajectory. And that's the service arm. And we have got on our target arm, the segment of the mirror that has been attached onto this robot, and the other half of the docking mechanism. So this target arm is very special because it has got a software system that mimic the microgravity. So basically, you can move it. It is basically, it is like floating object in space. So basically, you can move it anywhere that you want within the reach of the robot arm. Actually, on top of the both target arm and service arm, we have got these glowing balls. It's been attached to a separate system, including 10 cameras around the ceiling here, which actually pinpoints the exact position of the target arm and service arm in a live mode, real-time mode, that you will see. You will be shown how it works in our experiments, basically. So we have got, using that system, we have got a ground truth, and we have got validation and confirmation of how the docking system, docking mechanism works in our operation. So I stop now. We can start the initialization and running of the system. Thank you very much. And now we start a rotation on one of the axes of the target arm. Basically, these type of rotations are very common in any object that doesn't have a propulsion system in orbit. So basically, they're floating in, orienting in one of the axes. So just wanted to show you that how it happens in space. The sinking phase normally happens before our short-range rendezvous and docking. So it is a procedure that we assume. So now our algorithm is working on the. Yeah, I think it's been generated. Yeah, we have got the green light for our robot system to start. So it's starting the rendezvous to approach the target. See, I explain again, this setup that you see is much more, 10 times more brighter than what we normally do. So I'm not quite sure if our camera actually can fully recognize the position of the QR code that we use for the positioning and location, finding the location of the target arm. So yeah, gonna go to the scene and explain, because the latching hasn't happened. The latching with the autonomous system that sense that if after successful docking, it automatically close the latch and lock two systems. I'm not quite sure if you can see here or not, but the service arm is roughly 2 centimeters off of the target arm because of the lighting condition that we reproduced here. It is a very hard lighting condition, and it couldn't actually do the successful locking. It is like 2 centimeters off. So I'm going to reduce the lighting condition and reset back to the initial position and do another run to see if how the difference.
So I'm just confirming that people can see that the misalignment due to the challenge with the visual, because we have one of the screen showing quite precisely how the software is now understand the actual docking is misaligned. So that's very useful. Okay, thanks. So that's a very good demonstration of the challenge that Sam was describing earlier to answer the question from one of the audience. So now, that will be typically in cases like this in real missions, the system has a very safety measures to allow that the withdrawal and the reset and the rendezvous often has to be achieved. So typically that the algorithm that will look at recalibrating the parameters, or for example, there will be a decision made to abort that particular operation when you have two major light extreme sources and inform the mission to re-engage at the when the condition improves. So I think just to help you appreciate, how this extreme lighting condition would really mess up visual sensors, and giving the requirements of the accuracy that we need, and the mission team or the mother spacecraft will be informed. Okay, so what the team is doing now is with that incidents being picked up and detected, so the spacecraft will wait for the
Okay. So what you can see here, I wanted to show the difference between the lighting conditions. So now we see here, I want to show the difference between the lighting conditions and the previous version. Now I'm going to normal that we normally use, and so now
basically what's
going to start
created just now is what quite typical in space, where you just have some stage of the mission that you just have to abort the operation for the docking, and now it's been reset. Over to you, Sam, if you would like to talk me through.
All right. So as Professor Young explained, this is the typical rotation that you see in orbit for any object that hasn't got any propulsion system. Now the rendezvous started basically. So the system, the AI-based system, actually generated the algorithm for the approach. So you're seeing the approach at the moment. The current speed that you see might not be the nominal speed, but for our health and safety things and the lab experiments, we normally try to do things in a way that do not damage anything if the experiment goes wrong. So basically, doing it in a pace that follows our. So now the rendezvous finished and the approach has finished. So it is a latching time. So yeah, I can hear it now, but I'm not quite sure if our audience can hear it. The automatic system actually activated and it is latching. The latching is now completed. So so the docking has now completed, but due to health and safety features of the robot that we have, we are not able to move those docked parts together, because it automatically stops us. The safety features of the robots stop doing that. The only way that it can be happening at the moment is I come here and push these buttons, 2 buttons here, that actually would be able to move these docking. You can see that they are fully docked and they're attached to each other. And that's part of the mission. Basically, after docking happened, the service arm will take those segments of the mirror and move them with the satellites in a position that it's supposed to be there.
Actually, Sam, just if you could rotate also, yeah, great. Yeah, just to show that the rigidization post-grasping is extremely successful, because you can see that object being very, safely docked by the manufacturer of the servicing arm. And you can see the motion where you have to imagine that that object is in free floating mode, and the passive arm is clearly not blocking anything at all. This is very good. We actually have a very good question, in fact more than one question coming through the chat from Alec. So just to read it out to our team here, so we're just going to try to address them one by one. Okay, so there's a question about using fiducial marker instead of deep learning techniques. So basically what we have shown today is, because it's a cooperative target, meaning it's a target that we have knowledge of, we'll probably launch it with the servicing arm. So there are existing design of the target, there is knowledge of existing design and docking interface. So fiducial markers are definitely very realistic solutions. And as you've seen from the demo that we have shown, using actually very simplistic design of fiducial marker, we can achieve the docking very accurately and quite precisely. The deep learning are typically used when we have a non-copy target. I think people who follow work from our lab, and particularly we have a lot of YouTube videos about it, then deep learning definitely would be a good choice, because with non-copy targets such as space-gate bridge or retired satellites, which we have very limited information of, or perhaps inaccurate historical information of, then the deep learning technique really allows us to enhance our modeling adaptability in real time by, for example, training neural nets offline, so that the network can try to capture some very complicated, complex interlinkages or dynamic behaviors that was not previously known to the spacecraft, and then using it online would enhance the adaptability. So that is a very good question there. So moving on to another part of the set of questions from the same audience. What do you think is the best tool to recognize objects before attempting servicing? Do you know what you will repair? This is very interesting. So today we have shown a particular task in orbit operation that is to do with assembly of large space telescope, and similar techniques or methodologies can be transferred to satellite servicing, because basically you're looking at a target. So the question here relates to the recognition phase of that process. So this is very interesting. So it asks best tools to recognize objects. I presume when you say best tool, you might be referring to different type of algorithms to perform the object recognition. So typically that process needs to start with detection. So you have to first detect, and then you recognize, so meaning compare what you detect with what's in your database. And then you can perform the navigation, relative navigation. So from my point of view, I think we, as a research lab, we have actually a library of solutions. Solutions could include the more classical methods. You could look at fiducial marker. You could look at feature-based techniques. There are a range of machine learning methods that allows you to do the recognition. So basically classifying your object. I'm just looking at my team and see whether anybody wants to add to the answer to this question. If from their own experience. So this is looking at experience from us in terms of the object recognition or object identification. So
There's a follow-up question.
Sam, do you want to add based on your experience?
Just a little bit. Hi, Sam again here. There is no, actually, as Professor Young said, that there are a library of tools that we can use, and it really depends on specific mission. And
sorry, Sam, I'm trying to unmute you.
no, I'm using the same microphone as you, the camera. Yeah.
Oh, sorry. Yes,
Okay.
people can hear.
So the tools that we are choosing depends on the specific mission that you want to do. And sometimes, most of the time, there is not only one tool. So we need to have a library of tools, as Professor Yang said, and in our arsenal to use them just in case, because sometimes we need to have a very accurate position finding, and we use different tools. We use machine learning libraries and algorithms, and we use fiducial marker, we use LiDAR-based detection and positioning system, and we should have all of them at the same time. That's my experience about how to do that. So I'm hoping that I answered your questions. Thank you.
Thanks, Sam. That's very helpful. I'm just going to pull up further questions, which I think come from Abernav, who had a very good question earlier on. So this new question is to do with deep learning models and data set use for post-estimation, whether there are any data set available to the public. Could you mention any specific papers? That's an excellent question. Yes, indeed. So just a quick answer to the data set. We actually, in our lab, we use a collection of things for validation. So there are data sets that from real missions, I think, for example, something called SPEED. There are also data set we generate from the photorealistics orbital simulator that we develop in-house, which are deemed very realistic data sets for validating navigation algorithms such as for post-estimation. Indeed, we have a lot of published resources for colleagues who are interested to use. I'm going to put on the chat some YouTube videos where also included publication links to publications where you can get access of the paper. You can also look into the reference there where we tells you where to find those data sets and what evaluation matrix we use, so that if you have your own solutions and you want to compare with ours, then it's a good place to start. So I'm going to put that in the chat box as an extension to my answers. I will do it shortly after we finish answering all the questions. Again, a very good question there. Okay, so we have another question I'm going to put on the screen so everybody can see it. Do you prefer camera in visual ranging or something like LiDAR? Excellent question again. So of course, there's a difference between laser-based ranging sensor and also optical-based. Again, it depends on the actual stage of the mission and the requirements in the accuracy and precision of the mission. The difference can also comes in because of the power requirement between using laser or optical sensors. For optical sensor, you have monocular camera, also you have a stereo camera. They then can do the ranging differently in terms of the ranging distance and the accuracy. So as a general comment, of course, laser, in a general sense, I'm not saying any specific model, but in general speaking, if you do want to do a kind of ranging in the three-dimensional space, and LiDAR tend to be more power hungry, from just purely because maybe due to the hardware. For the camera, of course, you have the monocular camera for ranging or the stereo. Then there's a difference in the performance. So as space roboticists, we don't tend to discriminate sensing methods from either optical or light laser-based. It's more as overall system evaluation. Okay, we need to look at the overall evaluation of the sensors and make a decision on which ones we use. But what I can say is that we have an overall aim that is to try to reduce, optimize the computational requirements. So for instance, we have previously looked at using RGBD sensors. I said for those who are familiar with RGBD, it's basically a technique that use the optical sensing your RGB channels, to get your data from the optical sensing, but you are adding additional depths, which could be through laser-based, infrared-based, techniques. So this is almost like a compromise between a fully optical instrument or laser-based instrument. So I would say, depending on the capability of your processing power, your electrical power limitations of all the spacecraft, then we will choose among these methods. With LiDAR, for example, we did a lot of work in terms of optimizing the point clouds data input from laser sensing, so that we don't have to rely on very dense point clouds, where we can use very sparse point clouds, which still give us the depths that we need without going through extensively the computation. Okay, great. So I think we probably finished all the questions, and what we'll do is we're going to, I'm just going to send all the links to the papers and videos, so that you can take a look, and they're more more detailed answers to the questions. I'm just adding in the chat how we can come through. Okay, YouTube playlist on the Opto side, and there will be further reference, I think, to the papers that I can add to the chat as well. I think there's an interesting paper. I think the first paper I'm going to put in the chat there, that you can see there are comparisons of different pose estimation algorithms based on deep learning, and how they're compared using the same type of data sets. I'm just going to add those. If there are any further questions, please put that in as I talk. Okay. Do we have time for any further demo, or probably we're running out of time?
Yeah, we need to wrap it up.
We can do like 5 minutes and then one thing.
I think right.
I think we can go in front of camera and say goodbye to everybody.
Oh yeah.
There was one question we missed from
Sorry, apologies. My colleague Alex just reminded me that we missed one question. Are space robots different from other yes, cool, fair enough. I can start with something, but then I'll hand over to my other colleagues who can add their answers. Well, I think the short answer is yes. Yes, they are different, because robots designed for space or the extreme environment in space has to really be able to survive the space environment in terms of harsh radiation, and also extreme temperature. So meaning it have a very extreme temperature range, so it could be as very hot or very cold in extraterrestrial bodies such as Mars, so like on Earth. So the hardware has to be built to survive those conditions. There's also tend to be vacuum where the robots has to survive, and of course the communication latency, which is a point actually maybe we kind of took for granted so far, but actually it's really worth mentioning. The fact why Sam and other colleagues are helping him to show you the demo today is that it's all autonomous, it's all the decisions made in real time, but this is because remote operation of space robot is actually quite unrealistic because of the communication latency. Even if you have a situation, maybe the latency is not that great, then you still have an environment that you have limited knowledge of. Therefore, you want something autonomous rather than rather than you have to remotely operate. So definitely they have to be very different. So Sam and others, do you want to add your own thoughts?
I gotta jump in front of camera again.
Actually, I was thinking Sam actually has a lot to say because he comes from a terrestrial robotics background, so he
Yeah, but you said most of the thing about the specification.
Yeah.
The thing that I want to add is when you want to buy a robot here, you normally know what is the application, and there are quite a few companies that you go and choose between them. But in a space, it is not quite the similar situation. There are companies that manufacture robots for space, but you need to go with them and explain to them what you want to do. And normally they make it from scratch for that specific mission. So basically, it is not just going to the shop and make a robot for research or for industry or for manufacturing and come back home. So besides those space conditions, harsh conditions that the robot must survive, there are lots of other specifications and things that needs to be met before you have the robot. You need to know what is your exact payload, what is the length of the arms that you want to handle any operation in a space, and how you want to launch it. Basically, it is important because it needs to survive the launch condition as well, extreme acceleration and other stuff. So it is a very complicated decision. Yeah, and as Yang said, yeah, they are very different from the robots that we normally use in manufacturing and in research. Yeah. Thank you.
I can jump in.
No problem. I think we actually time to wrap up. So I'm going to invite everybody back to the screen. And actually, I just put Claire's question there because I thought this is a good question to answer to conclude and wrap up today's session. So Claire asks, what is your favorite thing about your job? So I think we can go around. Not blocking anybody, am I?
No,
And we can maybe go around among us to answer Claire's question as a conclusion of today. So to me, I've been working in this area as a roboticist for over 20 years. The favorite thing I think is I have to say that every day give me the opportunity to work on something innovative, creative, that including, of course, working with my own thoughts, but also engaging with talents. All this talents. Our team members today were helping with a demo. So that's really so exciting, rewarding, and keep me going every day, even though the job. It is challenging, but that's what keeps me going. So I think everybody should have opportunity to
Hi.
share their view. What is their favorite thing in their job?
Hi, I'm a postgraduate student and I'm doing the supporting stuffs, and also it was my dream to work for a space lab, and also I'm really enjoying to support the space robots and all the other drilling instruments and all things. Thank you.
Great.
As a student who has never done research before, it's a great opportunity to learn new things. I mean, since it's been my third day now, I've learned quite a lot just from the experience of being here and having access to research papers that I have to read on the topic. I find that really rewarding and just a challenge that I'm trying to complete. And it's just amazing how much I could learn about an industry or an area that I knew nothing about or minimum amount from university, and be able to apply it to research where I would like to work in the future.
Yeah, so for me, I can step in as a technical support for some. I think it's great to see how it changes. So with each day we have new problems and new solutions, and then basically you can see how it evolves. So then you see that the robot can actually grasp the object, or can do it itself, let's say, right now itself, and then create something what, for example, humans in future can do it. So it's good. It makes life easier, and I think that's the most appreciated thing to do it.
Yeah, unfortunately, I'm the last person, and everybody said the nice things. So for me, the research environment on robotic is amazing, basically. So we do things, we think about the things that hasn't been done before. Although the competition is really high, so there are lots of other people like us around the UK and around the world that doing the same. But we do our best to be the best in this area, and we achieved a lot so far, and we're working to achieve more.
Just to take what Sam was saying, actually we're contributing to some number of real-world missions as we speak, isn't it? So we're, for example, transferring a lot of knowledge into the industrial sector, because what we do in the research lab is, from very low TRL up to TRL 4 and 5, then it's really the right timing to hand over to the industry who is going to develop real-world missions. And we are currently in the process of supporting a number of this kind of real-world missions moving forward. And some of the algorithms we're developing and tested in the lab here is going to eventually fly on missions, and that's really very interesting. Of course, it's difficult, it's hard, but the fact that we work not just among ourselves in the university setting, but we're working in collaboration with industrial companies, allow them to take the technology to a higher technology readiness level. Eventually they fly, they exist in space. So it's very exciting to be able to do that. So hopefully you guys enjoy this last 2 hours, but for those who couldn't be with us, you can pick up the recording, and of course you know where we are, so feel free to get in touch if you need to discuss anything. So thank you so very much.
Thank you.
Okay, take care.